Okay, so good evening. Welcome to the fourth live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Harshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be taking weekly live session for this course for the entire course duration. So, in today's session, we will first have a quick recap to the week three session that we concluded last week, and then we'll review the week 4 learnings. So the week 4 recordings were oriented towards understanding the axial behavior of reinforced concrete. So in this, we first had an overview of how a reinforced concrete system responds to axial compression and tension by looking into the stress and strain relationships. For concrete, we saw the application of Hognested and Thorenfeld's stress strain relationships in design, and for steel, we used a simple elastic plastic profile. Then we saw the application of theory by forming load versus deformation profiles for different plain and reinforced concrete sections. And we understood the role of concrete compressive strength and reinforcement addition in the reinforced concrete response to axial compression and tension. And finally, we saw some numericals related to the comparison behavior also, like plain concrete versus reinforced concrete, how they compare with each other. Okay, so today, along with the quick theory recaps of different segment, I will introduce you with several questions to challenge the understanding on subject. In total, we will have around 12 to 13 questions that we'll discuss, some theoretical and some numerical. And at the end, I will make myself available to solve any other queries if you had related to any assignment question. So last week we discussed about durability of reinforced concrete. We introduced ourselves to what durability means by looking into both ACI and IS based definition of durability. And then we understood this figure, how performance degradation happens over time and how which leads to end of service life of reinforced concrete. Then we saw you how using repair, rehabilitation, and retrofitting performance can be restored and service life can be extended using this green curve. How this is affecting the performance degradation over time. Then we saw we understood through we understood how durability degradation in reinforced concrete can come. It can come in two ways, either due to poor quality concrete or due to ingress of aggressive ions from surrounding. So we first saw a few examples of poor quality concreting, how it affects the durability performance, like honeycombing in this photo, inadequate cover thickness in this photo, and cold joint formation in this photo. Then we had a basic overview of different ways degradation of concrete can happen from external actions as simplified in this table. So there can be mechanical degradation due to abrasion, erosion, impact and explosion. Physical degradation is there, structural degradation is there, chemical degradation, biological and corrosion. So in this we had mainly focused on chemical degradation, corrosion and mechanical degradation in our session. Now, when we talk about ingress of aggressive ions from surrounding, it is affected by several factors which are classified in these three types: concrete cover quality, environmental condition, and transport mechanism. We had a brief discussion on all the three types, and then we discussed a little bit deep into transport mechanism, how these mechanisms are governed, and what are the factors which influence them. We talked about how we can improve the cover concrete quality in three ways, either by lowering the W by C ratio, by improving the packing density of aggregates, and by using mineral admixtures as additive. So in this, we also discussed how different chemical admixture also enhances the durability. In chemical ingress, we talked about different chemicals responsible for degradation in concrete. We looked into sulfate degradation, alkali silica reaction, freeze and thaw effect, and finally corrosion of embedded steel reinforcements due to chlorides and carbonation. We also talked about mechanical degradation of concrete due to erosion, abrasion, and cavitation. And at last, we discussed how durability is taken into consideration in the design of reinforced concrete. We understood this flowchart of performance based design. We talked about different durability indexing testings. Those were oxygen permeability, water sorptivity, and RCPT. We talked about different codal provisions: IS 456, IRC 112, and IRS 1997, and we and how they consider durability by setting limits on design parameters like W by C ratio, cement content, cover thickness, crack width, and initial iron contents. Okay, so this was our complete discussion from last week, which was oriented towards durability. Now, when we talk about reinforced concrete structure, it is made up of several different structural elements, which are mainly classified as beams, slabs, columns, footings, and staircase. Okay, now these elements are often subjected to one or more types of forces, like it can be under flexural force, it can be under shear force, it can be under axial force, or it can be under torsional force. So one can see how these forces appear in this image. So this is an example of compression, okay, which comes under axial compression, and there can be axial tension. Then there can be flexure, which will induce bending in the system. There is shear near the joints or the supports, and there is torsion, which will bring a twisting effect in the section. So while designing a reinforced concrete element, it becomes important to understand each of these forces, how they are affecting the reinforced concrete, and to make sure that the design system is capable of handling all the applicable forces. Okay, so it is not like the design system should just be able to handle flexure. If there is shear which is also occurring, it should be able to handle both shear plus flexure. So understanding each of these forces separately is important in that way. Okay, so in today's session, we'll talk about axial behavior of reinforced concrete. Okay, and in the upcoming sessions, we'll introduce flexure, shear, and in later sessions, and how they are designed and how they are taken care in IS code also. So let us look at the axial behavior of a reinforced concrete system. So when a reinforced concrete member is subjected to axial load, its actual behavior is combined response of both concrete and steel. So this image here that you can see, this shows both the perspectives. On the top image, one can see the actual member behavior. Okay, so this is my reinforced concrete beam where both material deforms together under the applied load. Okay, and below we have an idealized model where concrete and steel are represented by a spring, separate springs having stiffnesses Kc and Ks. So Kc is the stiffness of concrete and Ks is the stiffness of spring. Now, what this analogy is doing, it helps us to understand that concrete and steel share the same load. They share the load based on their stiffness and deformation capability. Okay, so this total load, it will be shared by concrete and steel based on their stiffness and based on their deformation compatibility and capability. So we can break down the behavior of reinforced concrete into two contribution. First is the concrete contribution, which will resist compression, and second is the steel contribution, where reinforcement mainly resists the tension or any residual compression after cracking. Okay, so, and for a given condition, so if for a given loading condition, the axial analysis is governed by two fundamental equations. First is the equilibrium of internal forces. So the total load that is acting on the system is the sum of loads carried by concrete and steel. Okay, this is equilibrium of forces. And second is the strain compatibility. So concrete and steel, being since they are bonded together, they undergo same axial deformation. So the total deformation in the system is equal to deformation of concrete is equal to the deformation of steel. Okay, total elongation we can say, or total deformation we can say. Okay, so these are the two fundamental equations that govern the design of a reinforced concrete member. Okay. Now, if we see how we determine each of these forces component, so we know force load taken by concrete will be equal to the area of concrete times the strength of concrete. Okay, so this area is this AC is the area and this is the strength of concrete. And similarly for steel, load taken by steel will be area of steel times the strength of steel. Now how we determine strength of concrete? We can determine if we know the modulus of elasticity and the strain value at that level. Okay, and for steel also the same thing, modulus of elasticity times the strain will give us the stress or the stress of taken by the steel. So total load P is nothing but PC plus PS, and deformation, that is we can write in terms of like the strain taken by concrete will be equal to the strain taken by steel will be equal to the total strain in the system, and that will define the deformation. So delta is the deformation and L is the length of my member. So if we know the strain in the system, we can determine the deformation in the system. And finally, using these both, we can calculate the total load and how it depends upon the strain in the system and different reinforced concrete parameters. Okay, now let us see each of these components separately. So first, when concrete is subjected to compression, we saw a couple of sessions ago, there is a linear increase in stress with increasing strain, then it slows down till ultimate load, and then there is a decrease in stress with increasing strain until there is rupture. Okay, so this is a typical behavior of a concrete, plain concrete. So at ultimate load, this is my ultimate load, this is my ultimate load, and this is my rupture. Now, the strain is usually of order 0.0035 at rupture, and at ultimate load it is of order of 0.002. Okay, and MOE, the modulus of elasticity of concrete, we calculate using this initial linear profile, which follows this relationship as stated in IS 456. Okay, so we have seen this calculation also, how using different methods we can calculate modulus of elasticity, and how in lab we calculate modulus of elasticity using static testing. Okay, so this was when concrete is subjected to compression. However, when concrete is subjected to tension, then we see a linear, there are three stages. Okay, first is the linear elastic stage, where we see that the stress is increasing with strain linearly, the same as compression. Then there is a linear inelastic stage where micro cracking starts. So we see a certain slowdown of stress increases, strain will happen. And then finally there is cracking where there is crack localization and rupture of concrete. Okay, so micro crack localizes, they convert into macro crack, they develop, and they finally break the concrete. Okay, and we see a sudden drop in the load carrying capacity of concrete. Now, compared to compression, all these things they happen at a very small ultimate stress value. Okay, it is just around 10% of the stress that the concrete take in compression. Okay, so what graph you are seeing here, it is a very small portion of stress strain profile which will come up compared to compression. So that's why we use reinforcement in concrete to enhance the performance in tensile loading. So for steel in compression and tension, we assume a linear elastic plastic profile. Okay, that means that until yielding, there will be the stress will be linearly proportional to the strain, and post yielding, the stress will become constant. And this behavior holds true for both compression and tension. So in the first figure, you can see different stress strain profiles has been shown for different materials. So this A1 is for mild steel. Okay, so it is increasing linearly, okay, till yielding, and after yielding it has become constant. The same behavior has been shown in compression side also. And then there is cast iron, which also shows a certain linear behavior, and there is timber, and there is concrete. Okay, so for concrete you can see in tension, in compression zone it will show a good behavior, while in tension it will show very small stress versus strain relation. Okay, and the second figure is just a simplified version of the steel stress versus strain response that we are using for our session. So this slide just explains the tensile behavior of concrete when we talk about both plain and reinforced concrete. Okay, so on the left you can see plain concrete. So its tensile strength is given by the load taken upon the area of concrete. So we can see this behavior is quite brittle from this curve. Very small stress increase and very small strain capacity it is showing. So in the pre-cracking stage, we can see the material resists the tension linearly. However, as soon as the tension strength is reached, there is a rupture which happens with no significant deformation in the system. That means that the system will fail almost immediately after cracking. However, on the right, if we see the reinforced concrete system, the reinforcement changes this picture completely. So here we can see there are three stages. The pre-cracking stage, where concrete carries most of the tensile load, while steel shares a small amount of this portion. Then post concrete cracking and pre yielding of steel, where the cracks are formed in concrete but steel takes most of the tension while concrete is just contributing to the bonding. And then finally post yielding, where steel yields and undergoes large deformation and the stress strain profile becomes linear. Okay, so this allows structure to sustain load even after significant cracking has happened in the concrete. So while plain concrete is brittle in tension, the reinforcement ensures that there is ductility in load carrying capacity even after cracking, which is the fundamental reason why we are using steel in concrete members. Okay, now based on this basic theory understanding about steel and concrete and how they respond to axial compression and tension, just try to answer these three simple questions. In the meantime, if you have any doubts, you can ask. So I will keep myself mute for a couple of minutes so that you can answer the questions. Just type the answer in the chat box, whichever options you feel are right, and then we'll discuss. Okay, for question number one, in the stress strain curve of concrete, the descending branch represents, yes, the correct answer is D, the post peak softening and the brittle behavior. So you have seen till the peak, it is taking the load, and after peak, there is sudden rupture that happens in the concrete. Okay, in compression, there will be a zone of softening, and then there will be rupture after the ultimate strain value. While in tension, you won't see the softening phase. It will show a very brittle failure. Okay. Question number two. In reinforced concrete, the strain compatibility approach assumes. So the correct answer will be B. Okay, so we have seen in this last session also when we talked about the compatibility conditions. Okay, I guess a couple of sessions ago when we were discussing about design. So we assume that there is a perfect bond that exists between steel and concrete. So that's why the strain in both steel and concrete are the same in the entire loading phase. Okay, if there won't be any perfect bond, then the strain compatibility won't be there. The strain in concrete and steel won't be the same. Okay, so that is one assumptions we take in design. So can anyone tell me answer for C? Okay, I've seen few answers. Okay, question number three. The failure of an axially loaded short RC column is primarily due to. Okay, so yes, the correct answer is C. Okay, so when we talk about short axially loaded column, there is crushing of concrete which dominates the failure. Okay, buckling is something which happens when we talk about long RC columns. Okay, there buckling can be a reason for failure. However, steel failure generally doesn't happen because steel has more ability to resist stress compared to concrete. So it is generally concrete crushing that we observe. Okay, in short RC columns when it is axially loaded. Any doubts in these questions? Okay, let's move ahead. So we saw few slides ago this modulus of elasticity, stress versus strain profile of concrete under compression. Now, for a particular strain value, how to predict the stress in concrete? For this, we need certain simplified stress strain relationships. Okay, so for concrete having strength lower than 40 MPa, the Hognested stress strain curve relationship is used. Okay, it is commonly used for representing the stress versus strain profile of concrete when the strength is less than 40 MPa. So this curve is basically a simplified and widely used non-linear stress strain curve model that represents the behavior of concrete in compression, especially in reinforced concrete design. Okay. Now, why this is widely used? Because it idealizes the behavior of concrete before yielding and after yielding. Okay, like it idealizes the behavior under axial compression in two key phases. Okay, before yielding, that is the ascending branch, the parabolic part, which represents concrete gaining strength up till peak stress, and the descending branch, which is a linear, so it assumes a linear descending profile which represents softening and crushing of concrete post peak. Okay, and this representative equation for this curve is given by Fc upon Fc dash is 2 times epsilon c upon epsilon c dash minus epsilon c upon epsilon c dash whole square. So this Fc dash is the ultimate load. Okay, and epsilon c dash is the strain corresponding to the ultimate load. And knowing a certain strain, suppose I'm saying strain of 0.001. Okay, so at this strain we can estimate the stress taken by the concrete. Okay, so this is how we use this profile. Now, for concrete having strength more than 40 MPa up till 100 MPa, Hognested profile is not suitable. So, we use Thorenfeld's stress strain profile in such cases. So, this curve is like a refined non-linear model which is used to describe compression behavior in concrete, and it improves the earlier Hognested model by providing a more flexible fit to the experimental data, especially for high strength concrete. Okay, this is especially needed for high strength concrete. Okay, now you can see in the figure what is the difference, okay, between a normal strength concrete and a high strength concrete. So there is an additional strain hardening phase that you can see that comes in high strength concrete before ultimate strength, that is not there in normal strength concrete. And this additional phase is captured well by Thorenfeld's stress strain relationship. Okay, so this relationship is represented by this equation. Fc upon Fc dash is n times epsilon c upon epsilon c dash whole upon n minus 1 plus epsilon c upon epsilon c dash to the power n into k. Okay, so these two are the parameters n and k. N is the factor which accounts for curve fitting, and k is a factor which accounts for post peak decay. So these two factors are making this complex behavior of high strength concrete being captured properly. Okay, and so that this additional strain hardening effect can be captured. This is governed by the n factor, and this k factor takes care of this descending part. Okay, now to estimate the value of n and k, we use mirror method. Okay, so n is represented by this equation ec upon ec minus ec dash. So ec is the modulus of elasticity, ec dash is the modulus of elasticity at peak load. Okay, and that is equal to zero point 0.8 upon plus FCU upon 21.25. So this FCU, it is the cube strength, cube ultimate strength, concrete cube ultimate strength. If now EC dash we know, okay, for estimating EC we use this equation. Okay, and once we get EC and EC dash, uh, we can calculate n directly if we know this value, and epsilon c dash we can calculate. Okay, if we know the epsilon c value, and then if epsilon c, the strain that we are applying is less than epsilon c dash, we take this decay factor as 1 k. If strain is more than epsilon c dash, that means that we are in the descending profile. So then we take k value using this equation. Okay, so when we'll do a numerical, we'll just understand how this relationship is applied. For now, just remember that there are different relationships that has been given, which helps us to derive the value of n and k, and the value of k is dependent upon the where we want to calculate the strain. If we want to estimate the stress at a strain value lower than the ultimate strain, then the k value is taken as 1. And if I want to estimate stress at a strain value more than the ultimate strain, then the k value is calculated using this equation. Okay, and here FCU is the cube, concrete cube compressive strength. So if we have given cylindrical compressive strength, we'll convert it into cube by multiplying by a factor of 1.25. Okay, now based on these two theories, Hognested and Thorenfeld, just answer these three simple questions, and then we'll move into the numerical part. If anyone has any doubt in the discussion till now, they can ask. Okay, so for question number 4, which of the following statement is true regarding Hognested's model? So the correct answer will be D. Why? Because it assumes a parabolic profile. We have seen in this curve. Okay, I will just paste it here. So we can see here it assumes initially a parabolic profile and then a linear descending profile without any confinement effect. So we have seen when confinements are made, it increases the strength. So confinement effect is this strain hardening phase that we see in a concrete. That is something which what confinement brings on the table. Okay, so in Hognested profile, we don't capture accurately that behavior that we see in high strength concretes, okay, above 40 MPa strength concrete. That effect we don't capture properly, so that's why it uses a parabolic, simple parabolic then linear curve. So parabolic increasing and linear decreasing profile. The shape parameter n in the Thorenfeld's model is most sensitive to. Okay, so that this we have seen already in the equation. It is sensitive to the concrete compressive strength. Okay, so you can see here this n value is directly related to the strength of my concrete. Okay, question number 6. Compared to Hognested model, the Thorenfeld's model provides. Okay, yes, the correct answer will be C. So this we have seen in the first question here only. Okay, so when we talk about higher strength concrete above M40, we can see this additional strain hardening phase that comes, and this is something that is captured well by the Thorenfeld's model, instead of Hognested model, which just is a simple parabolic, which assumes just a simple parabolic profile. Okay. Now, just try to calculate this stress. The try to solve this question. So, in this question, what we need to do, we have a concrete specimen which follows a hog-nested model. Okay, we have given the ultimate strength. Ultimate cylindrical strength of concrete is given as 40 MPa, and strain at this is given as 0.002. So this is ultimate strain. I will write the epsilon dash so that it is not confusing. And I need to calculate the stress at an strain value of 0.0015. Okay. So you know this equation. Just give it a try. I will just copy this equation there. Okay. And knowing that this equation represents a hog-nested model, calculate the stress at a strain value of 0.0015. Did anyone do the calculation? You can just type in the chat box because I guess voice is breaking. I can't hear properly. What is the stress value you're getting at the strain of 0.0015? I will just show you here how this calculation is done. So in this equation, we know FC dash. So FC dash is 40 MPa. Okay, epsilon c is something that is given to us at 0.0015. Epsilon c dash is given to us at 0.002. Okay, again here epsilon c dash is 0.0015. Epsilon c is 0.0015 and epsilon c dash is 0.002. So when you will solve this equation, you will get Fc is equal to 37.5 MPa. Okay, so this is how we can apply Hognestad's relationship to calculate stress at a particular strain level in concrete. Am I clear with this solution? Yeah, 37.5. Okay, now give it a try to the second part. So this is the same in the Hognested model. Again, for same concrete, we need to calculate stress at 0.0024, assuming a linear descending branch from 0.002 to 0.003. So you have given the peak strain, ultimate strain, and the rupture strain. It is given to you, and you need to estimate the stress at a strain value of 0.0024 in between these two. Okay, and it is given, you can assume a linear descending branch. So how you will calculate this? Did anyone give it a try? Okay, so this is a simple linear equation. So if I can tell you by a straight line. Okay, so this is just like we have been given 2 points of this line. So this point, the top point we have been given, it is 0.002 strain and stress is 40 MPa. And at the lower point, we have given strain. Can you mute yourself? Yeah. And at this lower point, the strain is 0.003 and the stress is 0. So we can form the equation of line by using these 2 points. So we know how this is done. So how we get the equation of line if 2 points is given? So that is given by y minus y1 is equal to y2 minus y1 upon x2 minus x1 whole into x minus x1. So this is basically how we represent equation of a line if 2 points are known to us. Okay, so this is a basic mathematical expression. So here x1 is my strain value, which is 0.002. Y1 is stress at the strain, which is 40. X2 is 0.003 and y2 is 0. Okay, so these four parameters I know. So what I can write, y minus y1, which is 40, is equal to y2 0 minus 40 upon x2 0.003 minus 0.002 whole into x minus x1. So x is given to us, which is 0.0024. So 0.0024 minus x1 is 0.002. Okay, so the using this equation we can calculate what is y. Okay, so simple straight line equation. Okay, so upon solving you will get y will come out to be 24 MPa in this case. Okay, any doubt in this question? 40 is the ultimate load. After that there will be a linear decreasing profile, so stress will be lower at a higher strain value. Okay, 40 is at the peak. Okay, I have given this, we assume this partner in nested model that there is a linear descending profile. So that's why I represented that profile in terms of a linear equation joining 2 points. And the coordinate of these 2 points are known to me, x1, y1 and x2, y2. So using those coordinates, I've derived the equation of this line, and that equation I kept x is equal to 0.0024 so that I can calculate corresponding y. Y is my stress and x is my strain. Any doubt? Okay. Now just give it a try to this question. So now we are moving into Thorenfeld stress strain relationship. So a concrete sample follows a Thorenfeld stress strain relationship. Okay, I have not shown in the figure. Figure is here. I will just copy. Okay, figure is not there. Okay, it follows a Thorenfeld stress strain relationship, and for this concrete sample, we know the compressive strength of concrete. FC dash is given to us. It is 55 MPa, and strain at which we need to estimate the stress. It is given as 0.0024. So we need to calculate what is the stress at the strain value if we know the compressive strength of concrete. Okay, and I will just clarify here. This is cylindrical compressive strength of concrete that is given to us. Now just give it a thought how it can be calculated. I'll just copy the equations. So this is the basic representation, and for n and k, so these four relationships we use for calculating the value of n and k. So everything is given to you, just give it a try. Okay, so if you see here, we know FC dash. Okay, this is FC dash. Okay, this we know. And we know epsilon C at the strain at which we need to estimate the stress. We don't know epsilon C dash, we don't know the value of N, and we don't know the value of K. Okay, so if you see here in this equation, I'll just reduce the size so that I can copy here. Okay, we can estimate N since we know the compressive strength, but this is cube compressive strength. So what we'll do, n will be equal to zero point 0.8 plus, how we can convert cylindrical compressive strength into cube, by multiplying by a factor of 1.25. Okay, so 1.25 whole upon 21.25. Okay, so this will give me the value of n. Okay, so if you do this calculation, you will get a value of n is 0.035, 4.035. Now, I also need to calculate the value of epsilon c dash that is not known to me, for which I have this relationship. Okay, now in this relationship, FCU we know, and we know, we don't know the modulus of elasticity of concrete. So for this, we will use this relationship, the second relationship. Okay, so density of concrete is generally 2400 to the power 1.5. We'll take then point zero three five factor it is given to us, and then finally under root FCU. Okay, so this again it is cube ultimate strength, so that we have calculated 55 into 1.25, this is 68.75. Okay, this value 55 into 1.25 we will calculate, it will come out to be 68.75. Okay, so using this we calculate the value of EC, the modulus of elasticity of concrete, so that will come out to be 37505 MPa. Okay, now we know the value of EC, we know the value of N, and we know FCU. So we can calculate epsilon C dash. Okay, what is the ultimate strain? So that will be zero point 0.8 times 68.75 divided by 37506. Okay, whole into N 4.035 divided by 4.035 minus 1. Okay, so using this equation, we can calculate the ultimate strain. And the strain value, if you will see, it will come out to be very close to 2.00195. Okay, So this is the strain that you will get. Okay. Now, since my stress strain at which I need to calculate the stress, it is more than epsilon c dash. So I will use the second equation to calculate the value of k. Okay, so k will be given by 0.67 plus 68.75 divided by 77.5. Okay, and this will come out to be 1.557. Okay, so this is how we use this mirrors method to calculate the value of n and k. Okay, if just I know the strength of concrete and the strain at which I need to calculate the stress. Now we know all the values, so we'll just substitute in this equation. Okay, so Fc upon Fc dash we know it is 55 is equal to 4.035 times epsilon c upon epsilon c dash. Okay, so epsilon c I'm just directly it is I'm assuming it as very close to 0.002 so that I can simplify the calculation. So epsilon c upon epsilon c dash 0.004 upon 0.002 will give me a factor of 2. Okay, so this whole upon n minus 1 4.035 minus 1 plus 2 to the power n into k 4.035 into 1.557. Okay, so this is how we can substitute all the values, and from here when you will do the calculation you will get fc is equal to 5.49 mpa. Okay, so in this descending part, the strength will reduce up till 5.5 MPa. Okay, in this part, descending part, the strength will reduce up till 5.5 MPa when strain reaches 4.004. Okay, so this is how we use for Thornfield strain relationship for doing calculation. Okay, if the strain value was 0.001 or 0.0015, then the k value would that we would have taken would be 1. Okay, so the calculation will be accordingly changed. Okay, any doubts in this calculation?
For value of k, the in lecture note it was 0.67 plus fck divided by 77.5.
No,
But we
there
write
we have
fcu divided by
mentioned that
7.
correction that we need to do. I guess sir told the correction somewhere that this is not FCK, this is all this FCU.
No, for n value he say it is fcu, but
No,
for k
for
value
all
he
it
say
is
it is
FCU.
fck.
For all it is FCU.
Okay.
Okay, I hope this question is clear. Okay. Now, so if we need to estimate the load versus deformation profile for a reinforced concrete system, knowing how we can estimate the stress in concrete at various strain value and knowing how we can estimate the stress in steel at different strain value, we need to follow the following procedure that I have shown in this flow chart. So initially we'll choose a value of strain, concrete strain. Now this strain will be same as the strain in steel also and the strain in the entire reinforced concrete system. Okay. Now at the strain value, I'll find the stress in concrete and stress in steel due through constitutive models. So for concrete, the model that I will choose will depend upon the grade of concrete. And for steel, we know a linear stress strain profile that we use. Okay, so this is the profile that we use for steel that we'll stick in this part in this session. Now, corresponding to the stress that we get, we can calculate the load by multiplying with the area. Okay, and we can calculate the axial deformation. So deformation by length is equal to the strain. So deformation will be nothing but strain into length of the member. And once we know the deformation and we know the load, we can plot the load versus deformation profile. Okay, so let's see application of this flowchart in this question. So in this question, we need to plot the load versus deformation profile for a plain concrete subjected to both axial compression, axial tension. So you have been given a cylindrical concrete cylindrical strength is 25 MPa. The cross sectional area of concrete is given as 300 cross 300 and the length of the member is given as 1 meter. Okay, so this is like a beam. Okay, 300 cross 300 is the cross section. This length is 1 meter and the grade of concrete is 25 MPa, and it is subjected to both axial compression and tension. Okay, so for this you need to form the load versus deformation profile. Just give it a try. After a couple of minutes I will tell you the solution. Okay, so we have seen everything right now. Okay, just using that knowledge that you have seen, just make the compression profile first and then the tension profile. So choose different values of strain and then try to make calculate the load and the deformation. Okay, let's see the profile. We need a profile. At various strain value, we need to calculate the load. So what you are saying, it is the load which the concrete will take at the peak strain. So it will be corresponding to the stress of 25 MPa. So 25 into divided by multiplied by the area, you calculated the load. Okay, that is the peak load. For profile, we need load at different deformations. Okay, so that we need to plot. Okay, let's see. Okay, so let's choose. So we know that peak strain is 0.002. So let's take few points below the peak strain and some points above peak strain to calculate the stress taken by concrete at those points, and then we'll calculate the load and the deformation. Okay, so first let's take strain as 0.001. Okay, so we know this concrete FC dash is less than 40 MPa. So which profile we'll use? We'll use the Hognested profile. Okay, and for Hognested profile, we know the relationship. This is the relationship. So I will just copy this relationship here. Okay, so now, for strain of point 001, if I will do this calculation, how it will be, FC I know. Okay, so it will be nothing but FC dash is fixed with us. It is 25 MPa. So I will just change this to 25. Okay, and the right hand side will change as 2 times epsilon c. It is 0.001, the strain at which we want to do the calculation, divided with the epsilon c dash 0.002 001 divided by 0.002. Okay, minus 0.001 divided by 0.00 square. Okay, so when you will do this calculation, the stress SC value will come out to be 18.75 MPa. Okay, now similar calculation we can do for other strain values also in this at strain lower than 0.002, so that we can get multiple points for load versus deformation profile. So I will do multiple calculation. Okay, I will do calculation at 0.0015. Okay, so at 0.0015, nothing will change in this equation, just these two values will change, the epsilon c value. Okay, and when you will do this calculation, FC dash, it will come out to be 22.06. Okay, so at 0.0015, I will do one calculation, and let's do one calculation at a lower strain. Okay, 0.0005. Okay, so if at I will do calculation at 0.005, so I will just change the strain value here and here, and upon calculation you will find FC dash will come out to be 10.94. Okay, so these are the points before up till peak stress. Okay, so at strain equal to 0.002, we know stress is 25 MPa. At 0.0005, it is 10.4 MPa. At 0.0015, it is 22.06, and at 0.001 strain, it is 18.75. Okay, now let's take one point after peak. Okay, so this was before peak. Okay, so if I take one point after peak, let's take strain of 0.004, which is more than 0.002. So if you will see the strain, if I will keep at 0.004, okay, so this calculation will come out to be 0. So 0.004 upon 0.002 is 2. So this will be 2 times 2 minus 2 square, which will be nothing but 0. So my FC dash value will come out to be 0 MPa. Okay. Now, after peak, we don't need multiple points. Why? Because we assume a linear descending curve. So 2 points are enough for us to plot the profile. So we know the peak and we know the minimum value. So like we did in this in this question, 2 points are enough for the post peak behavior. Okay. So this was for concrete under compression. Okay. So how we derive the load versus deformation from this? Okay, so we'll just create a simple table. Let me delete these equations. So what I will do, I will just insert a simple table. So this is my stress in MPa. This is strain. This is load in kilonewton. And this is deformation. in mm. Okay, so stress we calculated, it was peak was 25 MPa, then 22.06 at strain of 0.0015. This was 0.002, then 18.75 at 0.001, 10.94 at 0.0005, and at 0.004 it was 0. So how we'll calculate the load? Load will be nothing but stress times the area. Okay, so low stress is load upon area. So load will be stress times the area, and area we know it is 300 cross 300 mm. Okay, so this MP is Newton per mm square. So this will multiply by this 25 into 300 cross 300 mm. So this will give me Newton, and for kilonewton I will divide by 1000. So this will give me load in kilonewton. So this value, if you will do the calculation, it will come out to be 2250 kilonewton. Similarly, for 22.06 it will be 1985.4. For 18.75 it will be 1687.5. For 10.94 it will be 984.6, and at 0 it will be 0. And deformation is nothing but uh, delta by L is the strain value. So delta will be strain into the length, and length of member it is given as 1 meter, which is 1000 mm. So 1000 into 0.0002 will be 2 mm. This will be 1.5 mm, 1 mm, zero point 0.5 mm, and 4 mm. So using this, we'll get the compression side of load versus deformation profile. Okay. Now, what about tension? Okay. So, okay. So we know under axial tension, the strength of concrete is 8% to 15% of that in compression. Okay. That we have seen in past theory. Okay. So let's take a factor of 10% for this question. Okay, let's assume 10%. The tensile capacity of concrete is 10% times the compression capacity. So FC dash will be nothing but zero point 0.1 times FC dash. FC dash we know, which is 25 MPa. So this will come out to be 2.5 MPa. Okay. Now corresponding strain will be nothing but stress upon strain is equal to the modulus of elasticity of concrete. The strain will be stress upon modulus of elasticity. Okay. And how we can calculate modulus of elasticity? Using the relationship 5000 times under root of FCK. Okay. So FCK to the power zero point 0.5. Okay. So this relationship we know, which is stated in the IS code. But in the question, we have given the compressive strength of cylinder, not cube. So FCK of cube will be equal to 1.25 times the mean strength of cylinder. Okay, so this is the mean strength that has been given to us. Okay, and we need to calculate the characteristic compressive strength. So we need to subtract 1.65 times standard deviation from this. So you have seen that probability profile of stress versus stress distribution. So the characteristic compressive strength, we take the strength above which 95% of the sample lies, and it is 1.65 times below the mean strength of concrete. And all this strength that we have given in the question, it is not mentioned that it is the characteristic strength. So we generally assume this strength as mean strength. Okay, and standard deviation we can take it as 5. Okay, we have seen in IS code it is taken as 5 for this grade of concrete. So it will be 1.25 times 25 minus 1.65 times 5. So this will give me strength of 23 MP. So this is the characteristic cube strength of my this grade of concrete. Now if I know this, I can calculate the ECD, the modulus elasticity of concrete, and this will come out to be 5000 times 23 to the power zero point 0.5. Okay, when you will do the calculation, you will get this value as 23979 MPa. Okay, once we know this value, we can calculate the strain in concrete. So it will be 2.5 divided by 23979. Okay, and this will come out to be point triple zero one zero four. So you can see what very small strain is taken by concrete under compression for this small value of load, which is very small compared to the peak strain that is taken under tension. Okay, so we know the strain and we know the stress value, and this is a linear profile that we have seen, and after this peak strain there is a sudden drop in strength, so we need to take only this point as enough for us. Okay, so what we'll do, we'll again insert a table to calculate the load versus deformation for this. Okay, so we have stress in MPa, we have strain, we have load in kilonewton, and we have deformation in mm. Okay, so stress is 2.5, strain is, I represent strain will be a negative sign, so point triple zero one zero four. Load is stress into the area, which will come out to be 225 kilonewton, and deformation is this strain value into 1000, so it will be minus 0.104 mm. And at a higher strain value, if I take a higher strain value of 0.002, we know it is a brittle failure, the stress will drop to zero. So I've just taken one additional point so that I can show in the profile how it is appearing. Okay, so at this deformation the load will turn out to be zero. Okay, now how we do this calculation, so I will just how we plot the profile, I will just open an Excel sheet. So this is my deformation on x-axis in mm, and there is load on y-axis in kilonewton. Okay, so all the points that we have calculated, we will just list those point here. Okay, so at deformation of -2, we calculated load is 0. At deformation of minus 1.04, the load was 2 minus 225. At deformation of 0, the load will be 0. Okay, at deformation of zero point 0.5, load was 984.6. At deformation of 1, load was 671687.5. At 1.5, it was 1985.4. At 2, it was 2250. And at 4, it was 0. So if I'll just plot this profile here, so you can see this profile how it is appearing. Okay, so this is the stress versus strain profile that you will see. So this is the parabolic plot in the compression side, which will drop as a linear profile after peak, and in the tension side there will be just a small stress that is taken, which will reduce to zero from here only. Okay, so from here itself it will drop to zero and it will remain zero thereafter. Okay, so this is the load versus deformation profile. On x-axis we have load and on y-axis we have deformation. Any doubt in this question? Any doubt in this question? Yeah, 1687.5 was the load deformation at 1 mm. At strain at 0.001. Did everyone understand this profile, how I have plotted this profile? You can see a proper Hognett
Yes, sir.
relationship coming. It is a parabolic and then linearly decreasing. Okay, let's just give it a try to one more such question so that we can understand the behavior. Okay, now just try to make profile for this question. So this is again a plain concrete. Okay, but this time this concrete is of higher strength. This is 60 MPa concrete. So here we need to use Thorenfeld's stress strain profile. Okay, the cross section is the same, the length of the member is the same. So I have kept the same cross section and the length so that later on we can compare both the profiles also. Okay, so just give it a try. Okay, you know the Thorenfeld's relationship. We have seen the application also. So just give it a try. First, calculate the value of n, and then k will be according to the strain that we apply, and then we'll see all other calculations. Okay, let's first calculate the value of n. Okay, so we know the concrete cylindrical strength. The cube strength will be 60 into 1.5. So 60 into 1.25, so that will be 75 MPa. Okay, so value of n will be zero point 0.8 plus 75, that is 60 into 1.25 divided by 21.25. Okay, so this will come out to be 4.33. Okay, now we know FCU, we know the density of concrete will assume at 2400. So 2400 to the power 1.5 into 0.03385 into under root of FCU 75. Okay, so EC will come out to be 39202 MPa. Okay, now we can calculate the peak strain of concrete. So that will be zero point 0.8 times 75 divided by 39202 times n upon n minus 1. So this will be 4.33 upon 4.33 minus 1. Okay, and this epsilon c dash will come out to be roughly equal to 0.002. So almost the same of what we get for a concrete having strength lower than 40 MPa. So we have seen that that strain value doesn't change much. Okay, we have seen in the previous question and also it was coming out to be 0.00195. So here it is coming out to be 0.002. Okay, so this is the peak strain. Okay, now the value of K, it will depend where we want to calculate the stress. So if the strain at which I am calculating stress is less than 0.002, then I will take the value of K as a 1, else I will calculate the value of K from this equation. Okay, so this value I will just calculate here so that we can use later on. So this will come out to be 0.67 plus 75 upon 77.5. So it will be 1.637. Okay, so if my strain is more than this 0.002, I will take K as 1.637. If my strain is less than 0.002, I will take K as 1. Okay, so again, like what we did in the last question, we'll at different strain value, we'll calculate the stress. Okay, so I will remove this calculation and I will add the basic equation of Thorenfeld's model. So first at strain value of 0.001, we'll calculate the stress. Okay, so since this is lower than 0.002, my K will be 1. Okay, and all other values I can keep. FC dash I know it is 60. Okay, so this will be 4.33 times this epsilon c dash upon epsilon c upon epsilon c dash will be nothing but 0.001 divided by 0.002, which is zero point 0.5. Okay, so I will directly use this factor as zero point 0.5 here so that I can keep a simple equation for understanding. Okay, so this I have shown here, epsilon c upon epsilon c dash, what it is coming. Okay, so 4.33 times zero point 0.5 whole upon 4.33 minus 1 plus zero point 0.5 to the power 4.33. Since k is 1, so I just need to take the factor as 4.33. N into k will be just 4.33. Okay, so upon doing this calculation, you will get FC value will come out to be 38.44 MPa. Okay, so this was for strain of 0.001. Similarly, we'll do the calculation for some more strain values like we did in the last question. Okay, so at strain value of 0.0015, this factor 0.0015 upon 0.002 will become 0.75. No, it will be, yeah, it will be 0.75. So my calculation will just become 4.33 into 0.75 upon 4.33 minus 1 upon 0.75. Okay, just let me do this calculation once. I have done the wrong calculation in my part. Okay, so this value will come out to be 53.83 MPa. Okay, approximate value there will be this. Okay, at strain of 0.0015. Okay, similarly we'll calculate at one more point until peak. So I will take 0.0005 also. Okay, so at 0005, this factor will become 1 by 4, which is 0.25. Okay, so I will directly just change this 0.25 upon 0.25, and all other things will be the same. Since my epsilon is still less than epsilon c dash, the key will remain 1. Okay, so the calculation will be 19.49 MPa this time. Okay, so this is how we use Thorenfeld's equation to calculate at stress at different strain. So this was before peak. Now what will happen after peak? After peak, my K value will also come into account. Okay. So what I will do, I will take two more points, 0.003 and 0.004. Let's take two more points. Okay, so at point 0.002, I already know the strain. So that's why we are taking two more points post peak. So point 0.003 upon point 0.001 will be nothing but 1.5. Okay, so I will do three changes now this time. 4.33 into 1.5 upon 4.33 minus 1 into 1.5 to the power 4.33 into k. So k we have calculated earlier. It was coming out to be 1.637 when epsilon, the strain is more than the peak strain. So I will take 1.637 here. Okay, now. Okay, so when you will do this calculation, so the stress will now reduce to, from peak it would have come down till 18.52. Okay, so you can see at just 0.001 increment from peak, there is a drastic drop in the stress of high strength concrete. Okay, so this we have seen in couple of lectures ago also, that we have seen that there is more drastic drop in strength of concrete in as the grade of concrete increases. Now for 0.004, this is 0.004, this factor will be 2, stress upon strain upon peak strain. So I'll just do three changes again here. This is 2, this is 2, and this is 4.33 into 1.637. Okay, so when you will do this calculation, it will come out to be 3.72 MP. Okay, so this is how we got 5 points, 6 points we have. Okay, at point 0.002 we know, I already know. At point 0.001, 0.0015, and point 0005 we have calculated the stress. So this will form the increasing profile, ascending profile, and these 2 points post week will give me the descending profile. Okay, so now we'll calculate the load versus deformation using these points. I'll just copy the table from previous question. Okay, so we have stress of 60 MPa at point 0.002. We got stress of 53.83 MPa at point 0.015. We got 38.44 MPa at point 0001. We got 19.49 MPa at point 0005. And then we got 18.52 MPa at point 003, and one more point we had 3.72 at point 004. So load will be nothing but area times the stress. So this is 300 times 300 times 60, and for converting Newton into kilonewton I will divide by 1000. So when you will do this calculation, it will come out to be 5400 here. For second it will be, just let me do the calculation, 4844.7. Then at this point 001 it will be 3459.6, 1754.1 at point 0005. At point 003 it is 1666.8, and it is 334.8 at this point 004. And deformation is nothing but strain times the length. So length is 1 mm, 1 meter, so it is 1000 mm. So this is 2, 1.5, 1, 0.5, 3, and 4. So these are different points that we have calculated for the load versus deformation. Now this was for axial compression. For tension, again, like how we did for the last question, the same thing we will repeat here. Okay, I will just calculate the same concept from there so that we can quickly solve this question. So we assume that in compression, the strength is 8 to 10% in compression, in tension. So we took a factor of 10%. So this time 10% of 60 will be 6.0 MPa. Okay, and the strain corresponding to that will be given by 6 upon modulus elasticity of concrete, which we have already calculated in this question. So we don't need to estimate again. We have calculated in the first part modulus elasticity of concrete is 39202 when we calculated the value of epsilon c dash. So we can directly use that value here. So 39202 we will use. So this will give me a strain of 0.000135. So we have seen that there is a slight increase in the tensile strength and tensile strain of concrete. Okay, so again we have 2 points. Okay, and we know in concrete there is brittle failure, so 2 points are enough for us. There is peak and then there is sudden drop in load. Okay, so we'll again take only 2 points. So stress is 6 MPa at a strain value of minus 0.000135, and stress is 0 at a strain value of higher than this. Okay, so any value higher than 0.000153, the strain will be zero. At the strain, the stress will be 0. So load, if I will calculate, so 6 into 300 into 300 divided by 1000, it will be minus 540, and deformation is point minus 0.153, and this is 0 and this is minus 2. Okay, so again we have all the points. So we'll do the same thing that we did in the last question. We'll form the load versus deformation profile. Okay, so I will just extend this. So I need deformation in mm and load in kilonewton. Okay, at minus 2 deformation load is 0, as at minus 1.53 it will be 0.153. Okay, at 0.153 it is minus 540. Okay, then at 0 it is 0, at zero point 0.5 it is 1754.1, at 1 it is 3459.6, at 1.5 it was 4844.7, at 2 it is 5400, at 3 it is 1666.8, and at 4 it is 334.8. Okay, in this previous question also, I guess this was the mistake. This is not minus, this is 0.104, not minus 0.124. Okay, so that's why you see very small response in tension. Okay, that was one mistake that we did. Okay, so for this again, if we will plot the profile, it will come out to be like this. Okay, so you can see in linear increase branch, then there is a slight strain hardening and then drop. Okay, so the drop is not linear this time. Okay, so this is according to the profile that we plot using Thorenfeld's model. Okay, and in the tension side, from here the stress will drop to 0, sudden drop will be 0 because of brittle failure. Any doubt in this profile? Any doubt in this question? How we plot the load versus
No,
deformation?
sir. Good.
Okay, so if you will see these two in comparison, okay, just ignore these 2 points. This will be like here, not here. I did it by mistake. Okay, so if you see both of the concrete grade, okay, we have the same cross sectional area and the same length of member. See how the load versus deformation profile can change. Okay, so I will just mark the correction here. So this is like from here, it is dropping till here and it is going like this. Okay, and for higher grade it is like this and then dropping till this and then growing like this. Okay, so this two profile you can change it like this. And in the compression side you can see for low strength the load and the deformation and for high strength the load and the deformation. So the peak is almost at the same part, but post peak you can see in the highest grade concrete there is more drastic drop in the load carrying capacity, while in low grade concrete there is a linear decrease that is happening in the profile. Okay. So for same cross section, this is how we can compare load versus deformation profile for different grades of concrete. And this is the effect of concrete grade. Okay. On both compression and tension side, there is increase. But that increase in the tension side is not that significant compared to the increase in the compression side. So that's why we say concrete is more contributing for compressive strength carrying capacity, while in tension its contribution is minimum. Okay, so this was all about plain concrete. Now, what if we introduce reinforcement to the system? Okay, so now we will plot a load deformation profile for a reinforced concrete. Okay, we will keep the compressive strength of concrete as 25 MPa. Any doubt? Yeah. We'll keep the compressive strength of concrete as 25 MPa, so we will use the Hognested curve. Concrete cross section is the same, length of the member is the same, but now we have provided reinforcements also. So FE 500 grade having six numbers of 16 diameter reinforcement is also provided in the tension side. Okay, so what is the effect of addition of reinforcement? We will see now. Okay, so just give it a try. Okay, how this will be solved now. So the only calculation that we need to think of is the addition of steel. What is the stress of steel in the system? And then you need to calculate the total load and the deformation. Deformation is the same, okay, because strain in concrete and strain in steel is the same. The deformation column won't change. It is just the total load carrying capacity that will change. Okay. So I will keep myself on mute for a couple of minutes. Just give it a try and then we'll see the solution. In the meantime, if you have any doubts, you can post in the chat box. Okay, let's see the solution. So there are some things that we can take from the previous part only. So this profile we can simply copy here. Okay, the initial part that was for just for concrete. Okay, so we'll see how we can modify this table now. Okay, so for compression, this is stress in concrete. One more thing that we'll add now is the stress in steel. Okay, at this strain value. Okay, so I will just add one more column here. So stress in MPa for steel. Okay, and then my total load will be stress taken by concrete plus stress taken by steel. Okay, so that I will modify. Okay, so this will change now. Okay, so for concrete part, we won't do the calculation again since we have done in question number 10. For steel, we'll do the calculation. Okay, now what is the peak strain of, so for steel, we assume this profile. If you have paid attention to the theory class. Okay, so this is the profile that we'll use for steel. Okay, so we'll use a elastic plastic profile. So till peak it is elastical, it is stress is proportional to strain, and then it is constant. Now what is this peak value? We can calculate simply by knowing the modulus of elasticity and peak stress. So we know modulus of elasticity is given by stress upon strain. Okay, so strain will be nothing but stress upon modulus of elasticity. So this peak strain, it will be nothing but stress which is 500 MPa upon modulus of elasticity which is 2 into 10 to the power 5. Okay, so when you will do this calculation, your strain value will come out to be 0.0025. Okay, so this is the peak strain. Okay, so till this strain, my steel stress in steel will be proportional to strain, so it will be modulus of elasticity times strain, and above this it will become constant at 500 MPa. So now if I take the strain as 0.002, it is lower than 0.0025. So stress in steel will be nothing but 0.002 times zero point 0.2 into 10 to the power 5. So this will come out to be 400 MPa. Okay, so this value will be 400 MPa. Similarly, at 0.0015, it is again lower than 0.0025. So 0.0015 into 2 into 10 to the power 5. Okay, so this value will come out to be 300 MPa. At 0.001, the value will come out to be 100 MPa, 200 MPa. At 0.0015, it will be 100 MPa. Now at 0.004, this stress is more than the strain. This strain is more than the yielding strain of steel. So now my yield strength of steel will become constant as 500. So I can take directly as 500 here. Okay, and at any above point, if I take the strain value of 0.005 also, the stress will be 500 only. Okay, so this will now become linear. Now what is the load carrying capacity? So it will be nothing but stress in concrete times the area of concrete plus stress taken by steel times the area of steel. So area of steel we can calculate. We know the uh, reinforcement in properties. So it is nothing but number of reinforcement, it is 6 into pi r square, so 3.14 into 8 into 8. Okay, and this complete thing divided by 1000 to convert Newton into kilonewton. Okay, so when you will do this calculation, this value will come out to be at 0.002, it will be 232732.3 MPa. Similarly, for all other at all other strain values, we know the stress in steel and stress in concrete, so we can calculate the total load. So this will be 2347.1. At this, it will be 1928.7 at strain of 0.001. At strain of 0.0005, it will be 1105.2. And at strain of 0.004, it will be 602.9. So you can see here it is not dropping to zero. Steel is there, which will still contribute to some stress bearing load carrying capacity. Okay, so this is for compression. Now we'll do the same thing for tension. Okay, so in tension again, we'll copy the table from the previous question, question number 10, and we'll see what is the contribution of steel there. Okay, so this thing for concrete will remain the same for us. This won't change. The change will only happen due to the addition of steel. Okay, so this is the strain. I will add this is due to concrete. Then there will be one more column here which will be due to steel. So this is stress in MPa due to steel. Will be remain same in both the cases, and load will change this time. Okay, so this value again steel, this epsilon y here, it is 0.00025 because we assume same linear profile in both tension and compression side. So the strain value is right now very low compared to 0.0025. So the stress will be given by nothing but the strain times modulus of elasticity 2 into 10 to the power 5. So this upon calculation, if you will do strain into modulus of elasticity, it come out to be 20.8 MPa. Now above this point, we assume that the concrete stress is zero. However, steel will still contribute in the tension side. Okay, so we'll have multiple points. So at the strain value of 0.002, it is lower than 0.0025. So contribution of steel will be 0.002 into 2 into 10 to the power 5. Okay, and this value will come out to be 400 MPa. Okay, at I will take more points. Okay, at minus 0.0025 we will take. So this is the yield point. Okay, so at this the strain stress in steel is 500 MPa, and above this if I take one more point, suppose 0.003 I will take. Again, my stress will in steel will remain the same because yielding has happened. Okay, and the contribution of concrete is now zero because only steel will contribute to the load carrying capacity. Okay, so if we do this calculation of load, it will be again 2.5 into area of concrete plus 20.8 times the area of steel. Area of steel and area of concrete we can calculate. Area of concrete is 300 into 300, and area of steel is 6 into 3.14 into r square, that is 8 into 8. And this whole we will divide by thousands to convert Newton into kilonewton. So this value will come out to be 250.1 kilonewton. Okay, for point triple zero one point triple zero 104. Then at point 002, steel is still contributing, so this is point 428.3. At 500 stress in steel, the load will be 602.9, and above this still, since concrete is not contributing and steel has yielded, the load carrying capacity will become constant. Okay, so this is minus 2.5 and this is minus 3. Okay, so if we take this to the Excel, if we plot this profile in Excel, let's see how this profile will come. Okay, so in the compression tension side, we have two more points now that I will add. So this is minus 3 and minus 2.5. Then this is minus 0.104, 0.5, and this is the same that we have kept. Okay, after 2 we had Up till 2 only we have plotted, because after that only steel is contributing, concrete is not contributing. So that will remain the same. Okay, so I will just copy the load values. So at zero point 0.5 it was 1105.2. At 1 it is 1928.7. At 1.5 it is 2347.1. At 2 it is 2732.3, and above 2 at 4 it is 602.9. Okay, we can add one more point here, 2.5 it is 602.9, and at 4 it is 602.9, because at strain of above 0.0025 the steel will yield, so the load carrying capacity will remain constant, like how we saw in the tension side. And in the tension at minus 0.104 it is 250.1. At minus 2 it is 482.3. At minus 2.5 it is 602.9. And at minus 3 it will be same 602.9, because steel has yielded. So if I plot this profile, you can see how the profile is coming. This is linear. This is right now, if I had plain concrete it would have dropped from here till 0 for, but now it has a linear increasing part till here, and then it is becoming constant. In the compression side it is showing a linear increase, then a parabolic increase, and then after peak strain it is showing a constant strain value which is taken by the steel, and the contribution of concrete has dropped till 0. Okay, so this is how we plot the stress versus strain profile for a load versus deformation profile for a reinforced concrete system. Any doubt in this? Any doubt in this calculation? How we did the calculation for reinforcement? So I just copied the past data from question number 10, because that I hope was clear to everyone, and I've just added the steel segment, what steel is doing in the in this deformation value. Okay, so if you compare now plain concrete and reinforced concrete, then you can see this change. Okay, so in plain concrete compared to reinforce, as soon as we add the reinforcement, you can see there is an increase in the compressive load. However, after peak, you can see there is still some resistance that the reinforced concrete will happen. Okay, offer. And in the compressions, in the tension side, you can see in case of reinforced concrete this graph would have dropped till 0. Okay, so this would have been from here, it would have dropped to 0. Okay, this is not right. From here it would have dropped to 0. However, for steel, for reinforced concrete, it is going, it is showing a increase in the stress profile, and then it is becoming linear. Okay, so this is the major change that the steel is doing. It is increasing the tensile capacity of the reinforced concrete system, and that we can clearly see in the load versus deformation profile. Any doubts? Okay, so this was all for today's session. Okay, so we first had an overview of axial behavior of reinforced concrete by understanding the stress versus strain response for both steel and concrete in axial compression and tension. We discussed about different models to interpret the stress versus strain profile of a plain concrete based on the concrete grade. Hognested model we saw for less than 40 MPa strength, and Thorenfeld's model we saw for more than 40 MPa strength. And we looked into how we can plot load versus deformation profile for a particular RC element if we know the dimensions and the length of the member under axial tension and compression. Okay, and we saw what is the change that concrete grade can bring and what is the change that addition of steel reinforcement brings. Okay, so as a practice you can do more such numericals. You can change concrete grade to further higher grade, concrete strength to further higher grade, and try to change the reinforcement area now and see what changes you will observe. Okay, thank you. Now if you have any doubt we can discuss.